Okay, so the first tool I'd like to talk, I think we need to keep the door open, otherwise we don't. The first tool I wanted to say a few words about is Valgrind. Okay, so Valgrind is a dynamic binary instrumentation tool written by Nick Nethercore as part of his dissertation research, in fact. So when an executable runs in a Valgrind, and it goes through these 4 steps that you see here. Okay, so you start with an executable, ordinary executable, okay, and when it's run on the Valgrind, then the actual machine code in that executable is not directly executed. Rather, it is analyzed, starting from the entry point of the executable. A piece of code is analyzed. It is translated into a higher level representation, something that is called U code, which is an intermediate representation. Think of it as like a high level RISC-like code. And in that, after the code has been translated into this intermediate representation, U code, then different skins can apply certain custom optimizations. Valgrind comes with a suite of tools for different tasks. Okay. So then this U code is enhanced, it's instrumented, so that is additional instructions are being added, maybe they perform some monitoring tasks, some checking tasks for a particular problem. And then the so enriched U code is then, using a just-in-time compiler, translated back into x86 code. And that x86 code is then run on the actual CPU. Now the translation here, this translation process doesn't happen for the entire executable at once. It's not that Valgrind goes through the entire executable, but rather it happens piece by piece and on demand. So it starts out with the actual entry point of the executable, very first instruction, and Valgrind scans forward instruction by instruction by instruction until it reaches a branch. And if it reaches a branch, the branch has a false root instruction, that's the next one, the branch is not taken, and one target of that branch. And what Valgrind would do here at this point is, the target of the branch would be, in this intermediate code, would be rigged such that it points back into the Valgrind runtime, but the false root branch would continue scanning there. So in essence, what it would give you is a straight shot. It's like a trace, a piece of the code that would be executed if the executable were started right at its entry point. So this trace, which you can think of as a linear piece of code, maybe with some branches that lead out from it, but they are short-circuited back into the runtime. So this piece of code is then instrumented and run, and then as it is actually run, one of two things can happen. Either it finishes, runs to completion, in which case the Valgrind looks at what the original code would have done next, or one of the branches in the code is taken. And in this case, Valgrind does the same thing, looks at where in the original executable would the code have jumped, and then it repeats the same process at this point. So you can think of the actually taken path traces through the executable as being instrumented in this way. All of this is under the hood. You don't notice any of this. Okay, what you see is that Valgrind performs certain monitoring tasks, maybe with a slowdown anywhere from 10 times to 100 times. Okay, with these instrumentation tools, it's easy to get slowdowns 3 orders, 4 orders of magnitude. So Valgrind needs to strike a compromise here between instrumentation effort and precision of what it does. Okay, so let's look at the first skin. The first skin is probably the most frequently used one. So the default skin is memcheck, and memcheck looks at uninitialized memory accesses. You have an example here. Other parts is an example. Okay, so here's an example C program. I have a function called getArray, allocates an array of integers. I have a function called SumArray that sums up the array, and then I have a main program. Let's start out with we'll just comment this part out. So how do you use Valgrind? Where you compile your program like you normally do. Then instead of running it like so, you run it with Valgrind like so. So then you get output. This is the PID. It says Valgrind memcheck, and this is just boilerplate up to here. And then if your program doesn't have any mistake, nothing would be printed. But otherwise, you get now diagnostics about what is going wrong with your program. So here, for instance, I'm getting invalid read of size 4. I'm getting backtrace where that happened. In this case, I'm not getting line numbers because I forgot to add with -G. Okay, so I'm getting line numbers here. This says, well, there is an invalid read of size 4 at 16, called from 24. And it refers to an address that is 0 bytes after a block of size 40, which was allocated by the new operator on line 8, called from line 23. Right? So what happened? There was an access with 0 bytes after 40 bytes allocated on this line here. And this access happened on this line. This was what, line 16 is here. Okay, so what's the problem? Why did that happen?
0 to 9 is
huh?
Then you have your
yeah, so it's off by 1 error, right? Okay, so this is a loop here. It says I is less than equal to n, but I passed 10 in it. So I would have to do either this, right? Or I have to pass in 9. Okay, let's say I pass in 9 now. Run it again. So now Valgrind doesn't detect any errors. Okay, it doesn't report any. It says for more details, it says errors, 0 errors from 0 context. Question for you, is the program correct though? So I allocate an array here, and then I sum the values in the array. Valgrind doesn't report anything. Okay, but let's say Valgrind, let's do this. Let's output the value the sum of s, right?
S is temporary variable, which means sum will be written there.
S is actually assigned here on this line.
That sum is the temporary variable and it will die after the local.
Sum is a temporary variable. You mean this one here?
No.
It's returnable.
How about the fact that it's not initialized?
Returning it to the int, not the address or pointer of that.
But I'm not using any pointers though. S is not a pointer. I'm not using any pointers. That's not the problem. The problem is what somebody else mentioned. It's not initialized. Remember, C++, new doesn't initialize anything. So interestingly, Valgrind didn't report that up to now. But if I run it again, now I'm getting this, getting a number of reports, 6 errors from 4 contexts. And if you look at these errors, what it says conditional jump or move depends on uninitialized values. Okay, and now you're getting a bunch of C++ templates. Okay. But let's look at the call chain. So the call chain is main, invoke the sorry, let me try this one. So if you look at this, it says main on line 26 invoke the output operator for an int, and then this is where the internal implementation starts. And on line 26 is where we output this.